Welcome back to Astronomy 201. Now we left ourselves with the following question. What are the evidence that the Earth is one that's actually rotating? Why isn't it the others that are rotating and the Sun is at the center? And that's a question that actually has puzzled scientists, thinkers, for thousands of years. And we know that at some point in time, people believed that the Earth was fixed at the center. But now today, we take it for granted that the Earth is rotating. But obviously the question is, why is that we now consider that the Earth is rotating? What are the evidences for that? Now, before we start with that discussion, before we look at the history that brought the ideas of heliocentrism from geocentrism, let's see what we usually, as people, actually see in the night sky. So what you see behind me is actually a simulation. It's simulation software called Stellarium. Stellarium is a freeware, so I'm safe. No one's going to blame me, even if that video goes on YouTube. And it allows me to simulate the sky the way you would see it. So imagine that this is a place in Lebanon. I've actually set the location to be in Lebanon. Now, obviously, the image is standardized, so that's not necessarily in Lebanon. You might find probably fields like that, and it's about noon on the 14th of February. So on Valentine's Day. I don't know what you did on that day. That's not my concern. For me, that's what is my concern. It's approximately noon. I didn't make it exactly noon. And how do I know that? Because it's exactly south. And I've chosen to zoom out so that I can actually see a larger vision of the sky, so that I see the east and the west for obvious reasons. Now we're going to see other directions too. Now the most common experience we have is to imagine that the sky is like a dome. After all, it starts at the horizon and moves all the way up above our heads. So we see it as a dome. And that's why people at some point talked about the celestial sphere. So they imagined that the sky is some kind of sphere that envelops the Earth. Now, obviously, it required that people started understanding the Earth as a sphere. How did we get there? That's something we're going to look at. For the time being, we're going to assume we're somewhere on Earth. We're actually looking every day at the night sky. And what do we see? Now, the first obvious thing is this one. I'm going to accelerate the motion. And well, you see the sun going in the west and rising to the east. And you've seen that the stars are actually doing the same thing, right? The moon is doing the same thing. Everything in the sky seems to be rising from the east and setting to the west. Now, if I change my point of view, I'm going to get back to my old regular, and I'm going to go at night, and I'm going to face myself south. So now I'm going to get it to the night because I need to see and stop. I'm going to face north, right? I'm going to see the whole sky above my head. And I'm going to start it again. Accelerate it again. Now, you have the impression that things are rotating. And if you look carefully, for example, at these stars called Big Dipper, notice that it was somewhere here. It's going like this, and then accelerate a bit more, and you're going to see that it goes, okay, day, and then again, it's as if everything is rotating around somewhere here. Well, that's basically what we call the North Celestial Pole. It's actually an extension, if you'd like to think of it, of the axis of the Earth and piercing through that imaginary sphere we call the celestial sphere. So basically what we see is the sky rotating from east to west. But that's not the only motion we look at. So I'm going to get back to my sun in the south, and I'm going to get back to day. But then I'm going to also. So I'm going to get back to noon. We're on the 18th of February. That's the day when the Martian lander Perseverance is going to land on Mars, sent by the United States, following Hope and uh, and Tianwen-1. So now we're almost due south, and the atmosphere is a hindrance for me. I'd like to be able to see the stars, and you're going to understand why. So I'm going to go back here, and I'm going to make the atmosphere disappear. So I blow it away. That's the interesting thing about simulations. So in this way, I can actually see the stars. Now, to be able to locate myself in a better way, I'm going to set up a frame. So I'm going to go to markings, and I'm going to ask it to show me something called the ecliptic. And I'm going to also ask it to show me the equatorial grid of the day. Voila. Now, notice that point here. And if I'm going to accelerate it again, you see that everything is actually moving around that point, right? And I'm going to stop. I'm going to go back to the sun and put it at noon. 1 day has elapsed, which is interesting because that's what I'm going to do now. I'm going to go 1 day at a time. It doesn't matter. And I'm going to actually zoom in so I can see the sun in a clear way. And to help me even more, I'm going to actually go on star lore, and I'm going to show the constellations. Just because they provide a frame and they actually allow me to visually understand where the different objects are. Now notice what happens if you go day after day after day after day after day after day. Now you actually see that relative to the stars in the background, they change, right, from day to day. At noon, same time, you see the stars, it's as if the stars are moving, but you could also imagine that the sun is actually moving right to the stars because the shapes you see drawn are basically the same. And the sun is, as we go, going, now this time in the opposite direction, it's going west to east. So the sun every day rises from the east and sets to the west. That's what we call the diurnal rotation. And we do see it across the year moving continuously from the west to the east relative to that background of stars. And if you look carefully, you're going to see that even the planets are doing the same thing. Fun, right? The moon is doing the same thing, and they're moving on that red line. Now that red line is something we call the ecliptic. It's actually the path of the sun in the sky. Okay, so that's the kind of motion we see. Now, just to find things, if I point to another object, if I'm going to draw another line on the sky, I'm going to draw a line called the equator. I'm going to say, wait a minute, we know what the equator is. Yes, indeed, it's the equator of the Earth extended, like the North Pole that's actually piercing the sky somewhere where we don't see the motion. Now, the blue line is the equator, and the red line is the ecliptic. So the sun is not moving on the equator, it's actually moving on a line that cuts the equator at certain points. Now, it's interesting. I'm going to just let it go, continue. Notice we're already in July, right? July 2021. And I'm going to show you what happens on that day. So I'm moving forward, 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 forward. We're 31st of August, and then 22nd of September, the sun is exactly at the point where there's an intersection between the ecliptic and the equator. Actually, if you're thinking it a bit, if I'm going to change that to Mars, so I'm going to change the months to 3. Oops, 21st of March, it's on the other point, because if you imagine that this is a sphere, this is a large sphere, these are circles. There's a red circle going around the Earth called the ecliptic, and there's a blue circle going around the Earth called the equator. And on the 31st of March, it's on the first point, and on the 22nd of September, it's on the second point. And these points are called the equinoxes. Fine. So that's the kind of thing we see in the sky. Now we do see obviously other things. Let me show you one last thing. So I'm going to move back to noon, right there in the middle. And I'm going to the motion of the sun. I'm going to call it vertically, so going up and down, up and down. In other words, if you're looking at the sun, I'm going to ask you to look at it here, going up and down. Okay, now we're going to see that the sun is actually going up and down. Now, but we're going to see over what dates and when does it reverse the direction going up and when does it reverse the direction going down. So let me go back again to my old position where I was actually speaking and come back to my diagram, and then I'm going to move month by month. I'm not going to worry too much. At some point, I'm going to actually increase that. So now we're in September, and oops, it went down, right? If you count the squares, you're going to see that it's going down. It's even lower at noon. Now, noon doesn't happen exactly at the same time, the solar noon. That's something we've understood last time, more or less. And then we're on the 22nd of December. Let me now go back that day and notice that as I'm going back in December, so I'm going to earlier dates, you see that the sun is going up. So as we go back to November, the sun is going up. Now I'm going to do it in the opposite direction. I'm just going back to December. The sun is slowly going down, going down, going down, going down, going down. And then I have the impression that somewhere here, it just flattened out. And now it's suddenly, as you see, moving up again. And the dates at which it's happening are around the 21st of December. So let's take it back, 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 back. And here we are. That's approximately where the sun suddenly stops going down. And then it's going to climb up again. Now you should basically already suspect when it's going to reach its highest point in the sky and when it's going to stop. At noon, again. So I'm looking at the position at the highest in the sky. And you see the sun is going higher from the south, from the S. You see the distance is increasing. We're already in May. And if you thought it out, you'd expect that to happen in June, on the 21st of June, the start of the summer. And then if I let it go again a bit, you see that the sun now is going down. But we clearly understand it. It's the sun actually moving on that red line called the ecliptic. Okay, so we've looked at some of the things we see in the night sky. If you play with the software the way I did, and you look at the planets carefully, you're going to see that the planets actually move like the sun from west to east on the sphere, relative to the stars. But there are certain periods, and you could compute them by looking at the year and the day they're happening. They're going to actually do a backward loop. That's something we call the retrograde motion. It's going to continue. So this is what people saw in the sky. This is what everyone was seeing. And that's why planets were called planets, because they were moving stars. They were just stars. You'd see in the background of the relative to the background of the star, and you see them moving relative to all the other stars. All the other stars are fixed relative to each other. Fine. So we just had an idea about what do we see in the night sky. Now we're going to try to understand how people explain things and why they end up with a heliocentric model later on. So see you in a short video. See you later.